Is the mic working? Okay. Hello, everyone. Welcome to the second talk of the afternoon. We have Anthony, postdoc from UC Berkeley and MIT, telling us about random local Hamiltonians, glassiness, and optimization.
Thanks for a very nice introduction. Great pleasure to be here. Well, I guess be back here, I guess. So I'm currently a postdoc in these places, and I'm actually paid by assignments, I think. And today I'll tell you about random local Hamiltonians. This is actually about 2 papers, and some of the author is actually here. The one that's already on archive is with Eric, Robbie, and Bobek. It's slightly more focused on fermions, but it also discusses probably random local Hamiltonians. And there the focus is more about the spin glass aspects of these models. And then I also mentioned another one that's in the same kind of topics with Joel, who's here, and then Alex. And this one is more on the on the optimization side, that also relates also uses Gibbs sampler in some form. This one will be appear soon. Okay, and let's get started. So I want to start with this motivating question. So suppose you have 100 logical qubits. Which system would you actually simulate? I guess who would do quantum chemistry? Maybe you can raise your hand. Okay, so some, right? Who would first simulate, I guess, dynamics? Yeah. I'm not going to go through all of them, but I just want to say yes. Everyone probably have their favorite models in mind. But perhaps it's fair to say there's not one definite model that everyone should simulate. Okay. And so the challenge is that currently there's maybe not a very clear sense of how you would prove such thing. There's no quantum computer, so then how do you know which one is sort of most classical hard and most quantumly easy? Right? It's not very clear. And so far, the argument has been a little bit more from computer science side. Then you can, if you go back to literature and then you search which problems has quantum advantage, it still don't have a clear answer, but then at least people would say, okay, here are some problems that are universal for quantum computation. So this is a very different kind of argument, but it still kind of says that, if you use this problem and in this algorithm, and in some cases, in these very special, finely tuned systems, then these are actually as strong as quantum computation. So this has got to be pretty hard. And then throughout the years, people just identify these pairs. Time evolution is closely tied to Hamiltonian simulation. Gap ground state is related to adiabatic computation, and local minimum. I think you'll hear about it tomorrow. So it's closely related to cooling, and so a very related thing is the stationary state and Lagrangian simulation. And you see that indeed, sort of a lot of the algorithmic developments. It's indeed kind of people do become these algorithms and just keep developing them. And however, I would say one sort of issue with this this existing approach is that even though we kind of play around with these two sides, what problem and what algorithm, we have played around with them quite a lot. It's not very clear if these kind of Hamiltonian William Lagrangian is the one that nature is actually doing. Right? These are coming from this Feynman-Kitov circuit to Hamiltonian mapping. Which is a very, computer science kind of very finely chosen Hamiltonians. Okay, so today we want to actually turn this approach to the other side, and instead we want to introduce a system that's arguably slightly more natural, still not very natural, but at least it's more like an average case problem. Okay, and that's really the title of this talk. We're going to introduce a system of random local Hamiltonians. More borrowing from how people have studied, spin glasses, and hopefully this would point us to some directions as, how do we actually think about what problems we're interested in and what algorithms can attack these problems. Okay.
I have a clarificatory question. So, like the first half of your slide, you are sort of describing things that I would describe as useful, right? You know, maybe I want to do Hamiltonian simulation to learn something about the Fermi-Hubbard model, whatever, its dynamics. I want to learn about the ground state. But now you come with a random model. So why does that fit into the same thing?
Right, this is kind of two parts that you hope them to be merged together, right? And in these models, you can study very well which problem and which algorithm. And then, but the place that you're able to show advantage is at some kind of not very realistic models. And here we know this part, since it has been explored, we just want to start here and then see what we can say. And then you can also ask the same question. Why do people study spin glasses? They don't look like the thing you really see in nature. However, it's actually becomes a very good test bed to study algorithms. And I guess to also answer your question again, the thing we actually explore here is about the thermodynamic properties and also optimization aspects. So that's still well defined. It's like a natural problem. Okay, so as I already said, the motivation of this talk is to borrow what people have did in the approach people have done in the spin glass world. I'm not an expert, but at least I can write down these models. So in the spin glass world, people have introduced this model. Like you just take all two-body Z. This is your constraints, and you put a Gaussian coefficients, and you sum over all of them, and let them be independent Gaussians. This is so-called SK model. And it's pretty simple to write down. It's not that easy to solve, but it's also not impossible to solve. You can also introduce a very natural variants of these models. And I would say, just throughout the past decades, it has been a very nice playground for theorists to test their algorithms in average case. So don't ask me more on this. I just requote this from my theorist friend who have worked on similar problems here. And the approach we're going to take is that, okay, this spin glass has been pretty successful. How do we do it in a quantum case as well? So we're going to just introduce very similar looking model, but now let's promote all the Z strings to quantum constraints, which are polys, for example. All right, so we start with Hamiltonian sum over Gaussian times matrices AI, and then we normalize it so that the variance is 1. Okay. And then the first example model we're going to talk about is random K poly models. Yeah, so you just pick all the possible poly with weight K. So all the X, Y, Z's, all the possible ones, and then sum over all of them. Okay. Local here means like degree K. So it's computer science local. It's kind of O2O. So in these models, we can get rid of as much spatial structure as possible. So the remaining parameters is K and N, and being the system size. And for example, if you realize this and K equals 2, this would be also sigma, sum over all pairs of polys, and then there could be X or Y or Z. So there are actually quite a lot of them. Okay? And then there's sort of no reason you will have to restrict to this, but for today, we kind of just stick to this family. However, you could also consider many similar variants. So for example, you could consider, whenever I want an X, there's another X that pairs up with it. I don't want any cross term, you could do that. And I think this is, looks more similar to this max-cut-like model that people have considered a lot, I think even here, in the worst case setting. But here we're just going to have Gaussian coefficients. And of course, you can also change the weights of, they doesn't have to be homogeneous. So you could just have all the, all different weights. And in very extreme cases, it's a Gaussian unitary ensemble. You just have all the possible poly strings. In this case, becomes like a big random matrix that loses the locality. Is this model clear? So here really what we're doing is just to promote z's to xyz's. Okay, so that's how you define this model. And then we're actually also going to consider the fermionic models, which might be less familiar to some people. So what we're going to do is to now put z's. We're going to put fermions instead of z's. Otherwise, it's the same. However, these fermions notoriously they anti-commute. So this is the sort of algebraic rule they obeys. Once you look at this, you realize when you swap two, it becomes negative. So when you do fermionic calculation, quite often you get lots of negative signs. If someone just told you this and then asked you what are the properties of this Hamiltonian, it's not a priori clear what should happen. Should it be very, very different from a spin place? Is it actually very similar? But it ends up being quite different. Yeah, this can be absorbed. I mean, just to make this consistent with, yeah. So you can forget this too. Yeah, so what about these models? What do people actually know? So physicists actually have done lots of calculation, at the physics level of rigor. And then they basically squeeze out all they can about this model, about its sort of black hole related properties. So don't ask me about that. But they basically get all they can get for what they wanted, but it has been very, very, very few rigorous results. So in the sense that you can write down theorems and lemmas. Yeah. So part of our goal is also just try to give more rigorous understanding of these models.
So what kind of rigorous results would one hope for here? Like a characterization of some optimization landscape, or?
Right, you'll see, because we're really just starting it. There's very, 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 very few existing results. People don't even know what's optimum, what the expected optimum are for these models.
Okay.
So there are lots of things you just don't know, like just like spectral properties, and then like how hard is it, phase transitions, completely.
So perhaps naive question. So physics has been looking at this, right? So, but why not the random party models?
But physicists also have, but this one is cooler because it's black hole. Right, yeah. Right, so somehow this particular model, there's actually lots of variants, but this one somehow is just ends up being the simplest that have all of the things that physicists care. So that's why people have beaten this model to death in the physical.
So by physics heuristics, you made the large end limit diagram essentially diagram.
Yeah, there's somehow leading order truncation scheme and then lots of exchange of limits and some,
And that leading order thing cannot be made rigorous. It's known that it's hard.
Physicists never, it's very hard to. Seems very not obvious how to do it. And there's also kind of saddle point approximation that you have some continuous integral, and then you say, this is maximized by this function. I don't know how.
Diagrammatic argument is really just counting orders of n.
Right. Yes, but that's who tells you that those are convergent? Yeah. So these two are the models we're going to focus on, Pauli's or fermions. K-body. Okay. Right, so just let me tell you the first result on this. So it's more on the glassy side. As the audience have asked, we're not really. There's really not very many existing results, so we're just really making baby steps here. But here's what we recently learned in this paper. So what we can show is that the Gibbs state is non-trivial but non-glassy. Okay, so it's a very intriguing title. Right, so let's take the Gibbs state and then rescale properly. So you would then just this is like a physical normalization. And here's a claim. So the Gibbs state at a very low temperature is non-glassy, whatever that means, but also have a circular lower bound. So the circular lower bound is that it means that any state that optimizes that achieves this energy requires a very deep circuit. So to be or just any state that achieves actually the same energy as a Gibbs state, including a Gibbs state itself.
The same or lower energy.
Yeah. It's really so. The statement sounds very much like like the NLTS type statement, even though it has very different origin. But I'll explain it more on that side. All right. So here are the numbers. Here's just one we get for both these models. So for Pauli's, it remains non. Okay, so let me start with the circuit depth. So this non-glassy part doesn't make it any sense to you right now. But here's what we get for the circuit depth. So claim that for any state with similar energies or below, all these states, however, no matter how you create them, must have a very deep circuit lower bound. And for the Pauli case, this is some number that grows with k. So if you fix k, this is a constant. Maybe this is not not so scary. However, for fermions, this guy actually grows with the system size. So this is really qualitatively interesting. So if k equal to 4, which is sort of the standard SYK, this is actually n squared.
What do you mean for long glassing?
I'll explain later. So we start here. Yeah.
In the circuit depth or circuit complexity?
So depth. So if you put in, we actually have a circuit size. We have an extra n. Oh. All right. So okay. So if you only consider very general settings, multiply this by n, and that's the number of parameters. Okay. So because the thing we have is like a counting argument, so it works for any fixed parameterized ansatz.
And it doesn't imply that like a lot of considers.
Okay, so if you have lots of considers, then yes. Here, assuming you kind of it's divided by multiplied by n, you get circuit size. Yeah, sorry, yeah, you're right. But this is really a counting argument. And just to compare, for classical spin, these are just just up or down, so you just one. The depth is just one. And so the other part, this non-glossy, what happens, right? So I'll tell you what this is, but this property holds at a very low temperature. For Pauli's, this is exponential in k, and then for fermions, this is also scaling with polynomial with n. So in some sense, these two seems to be kind of tied together. Yeah, and again, the normalization we chose is such that beta constant is like means constant temperature. So what happens here is that at some constant below temperature, Pauli's remains non-glassy. However, for fermions, this is actually all the way very down in the spectrum. So something really different is happening for the fermions.
This is circuit depth starting from
for any constant approximation all the way.
Starting from trivial products.
Right.
Can you talk about why you choose the square root n rescaling for the Hamiltonian? In the Gibbs state.
Okay, I mean this is just a normalization, but you can compare with the classical case, and this is sort of how you kind of a base point for classical things happens at constant beta. This is what a normalization does.
Okay.
So it makes the energy extensive. Because these models are frustrated, so then things scales like root n in some cases, so then you normalize it, add the extra n so that it's extensive. But you just compare these two. This is what classical is 1, and then this is exponential, and then classical is 1. It's just compare with the classical case. Right, so we can show that it remains this non-glassy holds from beta equals 0 all the way to at least this number. So it could actually go deeper, but this is this ground we get. Right, so some audience might be very curious about this NLTS kind of statements. I won't say they're not exactly the same, even though they sound kind of similar. But the setting is quite different. So in this NLTS setting, usually have fixed Hamiltonians. I think in many cases, like this code, things come from codes. And then, however, in our case, this comes from average case Hamiltonian, where we have lots of randomness. So the proof is, I would say, really very, very different flavor. With counting, then things are easier in some sense. But the thing I want to emphasize is that it also seems to be qualitatively different. So this kind of circular lower bound you get from code seems to be coming from kind of glassy behavior. Because code, there's lots kind of many states with similar energies, and some, and you kind of expect some energy barrier and some clustering kind of thing happen here. However, with our model, they seems to be more like random matrices and very non-commuting, and it seems that they're more on the other side of being non-glassy. Questions? Right. Okay, I'll do that. So, right. So here it is. Right. So so here's what I learned from what classical people have done. So here's the indicator of the glassiness. So it's kind of hard to define glassiness, but here's one indicator, a very precise version of this. So take the partition function, and then consider this guy. This is well defined, right? Log z and take expectation, and here log expectation z. Right? You can define these two numbers, and then people call the left-hand side to be quenched, the right-hand side to be annealed. I don't know why, but this one could correspond to more physical quantities. Log z is the free energy, and then you can do things here, and then could correspond to things you actually observe. And on the right-hand side, this is somehow, they say it's easier to compute because it's like expectation z, and then somehow this is nicer. And what happens is that if beta is very, very tiny, then these two would agree. However, at some point, they start to disagree in the thermodynamic limit. And then people say, okay, this indicates a spin glass phase transition. And then here it's kind of very heuristic, but you can also write down other notions of glassy behaviors. So now mixing time, this could be defined by its own. Algorithmic construction, people have defined some properties, along this direction, and then these, a lot of these spin glass notions. I'm not expert in them, but it's just like lots of spin glass notions, and this is one of them. Okay. Yeah, I think this one I might have to ask some experts on this. Yeah. But we just say, okay, here's the definition, and we can directly study this quantity. Yeah. So let me say, this is not a definite. Like there are cases where this disagree, but other things, this test, this guy is non-glassy, but other indicator is glassy. So they're not really definite, but he's just one indicator.
That has a lot to do with like what you'd expect to be the dominant terms, the ZB, because that sort of tells you something structurally about what you expect, the distribution to look like in terms of these, properties of replica symmetry breaking. But yeah,
thanks. So disagreement is a quantitative statement in the sense that for non-glassy systems, you expect when n goes to infinity, these two things are the same. Specifically, if all the coefficients they are positive, right, bounded away from 0, and
coefficients of what?
I mean, in the k-local case, right, the coefficients not of mean 0 anymore; they are all positive.
Well, okay, I don't know how you do that in those cases. Yeah.
With some randomness. And these two numbers, are they going to agree?
I don't know.
Then
Okay, I don't exactly know what's the right normalization.
I just want to know, what the two numbers, they are not the same. That doesn't seem surprising, but it would be useful to know that when do they actually agree means they are the same. You take two random instances and you take this here to expectation. Just
So I don't understand. I mean, these are two numbers, and then you can compare them.
compare them, yeah.
Yeah, and then they could be the same or not, when n equals infinity.
Right. When you say they disagree, which is bad, spin glass, right? But do you also know when they will agree, other than with the random coefficients?
I mean, so I presume you're going to prove that you're in the non-glassy phase. You're going to show that they're
The
close to each other up to
Yeah,
some
what we'll
fraction.
we'll just prove that they agree at
Yeah.
at small beta.
Kind of tell you how much they concentrate, right? These are random variables, and you exchange expectation with a nonlinear function.
That's right.
So if they
There's a log here. There's a log here.
yeah, they concentrate on the mean, then they should agree. They do not concentrate, so that's glassy behavior.
But when you say non-glassy, does that mean that you have a lot of local minimum but not exponentially many?
Okay, that's the interpretation. So this is what we can show. Yeah, and this is really the first step that we can show that we happen to be able to show, because that would be a next step. Correct. Yeah, I can because these are just two numbers that I can calculate, and then in the end, what we actually show is that these log z just concentrates so well that it doesn't matter where you put expectation. Okay, so here's what we show. We just directly sandwich these two quantities. So this bound they just always hold, and this bound is what we show. So we show that the error between these two quantities is bounded by this number. And for Pauli's, this number is decaying with k. So this is so for k Pauli, it still seems that this is not completely satisfactory. However, for fermions, this guy is actually decays with n. So when n is very big, this guy really goes to 0. And then for Pauli's, this is a constant that this will be a small constant. So you can choose what you want, whether you want to call this a node or not, because this quantity will be pretty small, but it will still be a constant. I think it's like convex, steel concavity, one of them. Yeah. Anyway, this is one indicator that people have used in spin glass literature. We really just take them, and then we're just able to prove this by basically proving log z is very concentrated. And then these depend somehow by the model with this parameter delta that I will tell you. And here are the values of these models. So this is just one indicator, but hopefully this may mean that these models are actually quantumly easy, sort of still at a low temperature. But this is not what we show here. Okay, we only just show that this number agrees. So now I've told you there's like a lower bound and there's this glassiness behavior. You might wonder why these two are why they're even related. And it turns out they actually come from the same quantity. And it all comes from the fact that these models are very non-commuting, which is a quantum behavior. So here's a key quantity. It's something that looks like a variance, but slightly more than that. So given a set of Hermitian operators, so we're just going to basically take these to be our favorite Pauli's or fermions. And we're going to consider this quantity. You're going to sandwich all these operators with your state, and then take squares, and then take supremum over a fixed input state. So it's always bounded by the square of the norms, but it could be smaller. Yeah, it's the same delta. Yeah. This quantity I've shown in quite different contexts, learning and then in the context of random matrices. And this one turns out to be very, very helpful in discussing all the properties of these models. So if you just look at this, not so clear what it does. But let me consider this example with Pauli's. So it turns out this quantity kind of measures how commuting they are, or the ability for a fixed state to simultaneously align with all these matrices. So for Pauli's, because X, Y, Z are kind of non-compatible, it's hard to optimize all of them. And then the best you can do is just this. And then you can do this for actually not just X, Y, Z, you can also do it for long Pauli string, and then you get different numbers. This one is decaying exponentially. And this is a direct calculation. And you can also do it for K Pauli strings are n-qubit, which is the case we care about. And this decays exponentially with K. And then to compare, if you have a bunch of classical strings, then this would actually just be 1.
All Pauli strings, and when you plug in n equals to 1, why does this 1/2 does not match with 1/3?
All right, this is K Pauli string is weight K.
Oh, no. I mean the first one.
Yeah.
So if you plug in n equals to 1, you have basically you have X, Y, Z.
Yeah, you have identity. Yes. Yeah. So if you have identity, and then these two actually matches. Yes. Yeah. Okay. Right. So that's Pauli. So what about fermions? So it turns out fermions for these numbers is actually much smaller. So in some sense, they're much more non-commuting. So recall there's this anti-commutation relation that physicists tell you, and then you can try to do this for fermions and or like these K-body fermions. And then this ends up being how it scales. This ends up being a more involved calculation. And this ends up, it's become quite involved, and you have to find you have to take these fermions and then consider the commutation relation of these operator. Basically, you draw a edge if the operators anti-commute. And then you have to really do a lot of calculation on the graph properties of this guy. Okay, so just suppose you just accept that this delta can be calculated, and it's very small. And how do we use it? And actually, it's not very far to get circular lower bounds from this commutation index, because if you just really literally evaluate the Hamiltonian with a fixed state, with our model, this really just recovers basically the same quantity. But it tells you if I have a fixed state and I put a value on a Hamiltonian, this is roughly the energy that it would get. And if this guy is very, very small, it means that it's just very, it's very hard for a fixed state to kind of point to the right direction. But you also realize this guy is a Gaussian variable. Right? It's if once you evaluate on the fixed state, then you can just plug in. This is a Gaussian with this variance, and then you can just plug it. Just go through like a union bound over the state any circuit generated state. Then you can get the circuit size lower bound. So this bound really just a counting argument for Gaussian concentrated.
Is there an intuitive reason why, during the calculation, like the cubic case and Fermi case are different? Is there intuitive technical reason?
Well, fermions are more non-commuting. I don't know. So even just take the case of single fermions. You have single body fermions. So they all pairwise anti-commute. But for Pauli's, it's a little harder to do that. They still kind of more or less commute. If you put a Pauli on each side, they still commute with all of them.
You mean there will be more time cancel each other, something like that?
They're more anti-commuting. It's hard to they're more uncertain. I don't know how to say it.
Intuitively, it seems that what you're saying is that the glassiness is kind of the same as frustration in this model. Is that also the understanding for classical spin glass?
Oh, for classical, these numbers are all one. This is really coming from non-commuting.
Right, but I was trying to understand where the glassiness will come from if you are thinking about classical systems. I mean, there was also frustration, of course, for classical spin systems, right? Is that from the same origin? Or?
Oh, okay, at least none of these don't work for classical.
Okay.
So I don't, yeah. I guess what's remarkable is that from this approach, we don't actually do really all this classical spin glass calculation. We just look at this quantity and then say, oh, this quantity is very small because it's hard to optimize all terms at the same time. And somehow that already tells us the free energy is very concentrated. Oh, I haven't shown you, but that's what this will tell you.
You have one comment saying that whatever you derive, it actually show that the circuit depths cannot be too shallow. I mean, can you elaborate on that? Why this is true? You said unibound, yeah.
Oh, right. So pick your favorite circuit family, and then you put an epsilon net on them. Then for each of them, this holds. So then the chance that substate get a very, very, very low energy where T is extremely large is very unlikely. It is epsilon net argument.
Here you maximize your energy.
That statement is for any fixed space size.
Right. So then you put a fixed epsilon net on your circuit, yeah, on your circuit architecture.
I was also wondering about like the question. So for fermions, is it also the case that if I just take a fixed Hamiltonian, I have the same circuit also?
Fixed Hamiltonian. No, this requires Gaussian random. All these argument requires Gaussian.
I know that the argument works for Gaussian. I'm just wondering if it's the case because my thinking is that fermions like to simulate them might even need like these long range strings because of the anti-function. So is that an argument why I already need like what I need that?
I think that seems very tempting, but I don't think it always works. I think you're probably very you can find an example where.
Like 1D. So.
No, I think here you really need randomness. Yeah, I think that is completely, for worst cases, completely different kind of argument. I also don't know if it would hold actually. Sorry, yeah, I don't know if it would hold.
Yeah, no, I'm curious.
Right, whatever we say about these models are defined for this model, and then how you extrapolate to other models, it takes your
I'm just trying to get at the reason between like the disparity between your two systems.
Right. So now if you accept that this commutation index somehow governs concentration, well, then you can also directly compute so I guess Lipschitz constants with respect to this random variable. And it turns out this is also bounded by this quantity. Just directly evaluate this, and you really just get this number. And yeah, so then somehow this free energy also well concentrated with a nice tail. Then this Chen and Nil agrees. Right, so I'll very quickly mention the other side of the result. So right now I just show you that this non-glassiness is it's some indicator of glassiness. If it's not glassy, then maybe it will be easy. And here we'll just give you some more direct algorithmic evidence about how that we can actually directly optimize these models. Okay. So here's a claim in a different paper. So we claim that there's an efficient algorithm that would prepare low energy states of these models, but it also enjoy the same kind of circular lower bound that I've told you. Okay, so this is like an optimization problem where your goal is to optimize this Hamiltonian. And this is the parameters we get. So this is the true energy is bounded by root n. It could be smaller. Then we show that you can get this number root n over k with the explicit k dependence. And previously, the best has exponential decay dependence on k. So you get like a better k dependence. And all the states that achieve the same comparable energy also have the similar circuit depth lower bound that I have showed you. Right. So previous, if you just want to optimize k-Paulys, you can actually just have product states. However, because these bounds actually decays with k, because product state is not super aligning with all these matrices. So in some sense, you already see there's a difference between product states and sort of quantum algorithms, and this is consistent with this circuit depth lower bound. And for fermions, the probably best is by Hastings O'Donnell. They have they have some quantum algorithm that I wrote down. It's a little hard to interpret, but chasing through the constants, assume that they also have this exponential dependence. All right, so this optimization problem. So we do better. Maximize. Okay, sorry, yeah. High energy state. Sorry. It is very confusing.
Why do you want to choose this convention to maximize that?
An optimization problem.
So on this slide, I replaced every low with high.
Yes. Yeah, I'm sorry.
There's still a circuit lower bound for it.
right. Okay.
Can you say again why I want to find a high energy state?
Well, I mean, you can do either. It's just like I think CS people like to say optimization.
Oh, now I remember.
Like a low score or a high energy.
I mean, your model is invariant to the sign.
Yeah, it doesn't matter. It doesn't matter. In these models, it's
I want the edge of it.
okay. So let me just show this picture. Okay, so it's centered at 0, and then it has a tail that goes from both ways. You can do either one. So right. So in this picture, this is optimization. Okay, and then we know that this from black box matrix concentration is always root n. It could be better. The true is kind of somewhere here, and we show that it's feasible all the way here. And it's actually conjectured that the true value is also scale with this with a different constant, but this seems a bit hard to prove. I'll tell you. It's a give something algorithm. Polynomial. For the fermionic case, it's polynomial. It's just different power, different poly n. Wait, here.
Sorry, the circuit depth for the K is that what you're saying? Or into the K over 2?
All right, this is a much deeper circuit. Fermions seems to be more complex in this way. Yeah. Right. So in the last minutes, I'll just show what the algorithm is. The algorithm, no surprise, is actually just running a version of just running a Lambadian, a one that's chosen depending on the Hamiltonian. And then what we do is to start with the maximum mixed state and then evolve it for a short time, and it stopped right there. Just because it seems hard to control. So this seems to be hard to control for a longer time. So we really just evolve it for a very short time. In fact, for a much simpler Lambadian, I will show you. And then this already achieved this advertised energy. And what's interesting here is that the bounds is actually the same for both Paulis and fermions. And it depends really about like some kind of local energy quantity. So it depends on this H local, which is counting kind of how many terms are interacting with one side. And somehow this number is the same for both Paulis and fermions, even though the commutation index is very different. So somehow the fact that fermions are very anti-commuting doesn't matter in this algorithm. And then here's the Lindblad.
So you're saying that your algorithm with a short period of time achieves an energy which is proportional to square root of n, is that correct?
Yeah. The constant ratio approximation of the.
What's the
Things like 1 over k, 1 over root k. Yeah. Yeah, in some sense, you're kind of locally applying a map. And then it's right. So okay, so here's the map you actually apply. So this is Lindbladian where you apply a local term for each site, where each of these k's are a baby version of Gibbs sampler, but the much truncated one, where this is a single site Pauli or Marianas, and then you just add like a little tilt where it depends on kind of this commutator. In particular, this doesn't depend on the full Hamiltonian, but only kind of the things that's touching it. And this is a hint at why its local energy is important. And this is coming from truncating Heisenberg dynamics, which is in some sense you can think of this algorithm as like a baby version of lots of consistent with lots of ones that people have proposed. But this one is slightly still more complicated, and we only do this simpler one. So I think it's just polynomially worse. So for fermions, it's polynomially worse. But in any case, this will all just be Pauli n. It just really depends on the Hamiltonian. You basically invoke the Hamiltonian for a very, very short time. Yeah. So here's a summary. I think I'm out of time. So today, we'll try to introduce some families of quantum versions of spin glasses. Really only pushing, getting some of the very basic results. There's certainly a lot more to be said, but here's a summary of what we get. We say it's classically non-trivial in the sense of the circuit depth lower bound. We say it's non-glassy in this very restricted sense of annealed versus quench-free energy. And it's quantumly easy in a sense that you can prepare a low energy state achieving these bounds. And then what's interesting is that these two different results relies on different different properties of the Hamiltonian. This one is kind of some local energy quantity, and this one is some kind of commutation structure. And they actually are different, very different quantities. And this one arguably seems to have more classical analogs, but this one doesn't quite seem.
For this optimization algorithm, which part that you use the fact that this Hamiltonian is random?
Oh, right. So the way we actually evaluate to get this bound is some very nasty calculation. You really take expectation and take derivatives, so it's very, very nasty.
But in principle, the algorithm should also work for like arbitrary local Hamiltonian.
Right, but then we don't quite know what the guarantee would be. Like here we can get constant ratio approximation because it's random. Yeah, I think if you have non-random, then the scaling could be very, very different.
I mean, for non-random, the benchmark of what you can achieve will probably be very different, right?
Right, yeah. For worst case problem, yeah, the tools will be also seems very, very different. These are average case, so then at least there's quantity we can compute. So here, in some sense, you're fixing the model, and then you can compute these numbers. Yeah. For worst case, we don't know how to whether there's like a common way to compare this.
What's the times that you need to run this Lindblad?
Constants.
So a lot of jumps have already happened.
Okay, roughly each spin is being flipped once, but it might scale with k. So it doesn't scale with n, but it might scale with k. So roughly what happens is that when you apply this Lindbladian, it kind of looks at all the terms, kind of all the, you kind of draw this flower on each side. You draw the Hamiltonians like this, and then this is what the algorithm knows, and you try to push kind of each of them at the same time. It doesn't use any of these higher order thing. You only sort of using this first order.
The time is so short. I mean, wouldn't some sort of local message passing something?
Yeah, I don't know. I think it would be okay. So it'd be very cool if you can also show that your favorite quantum algorithm or classical algorithm also work. I don't know. I think we'll be very surprised if the classical algorithm that can do similar things, because these terms they cannot touch everything all at the same time. So, but I think so I don't know. I'm somewhat skeptical with the classical algorithm can do it, but we'll come to dequantize this. And then just like some quick outlook, in our proof of non-glassiness is we only have one, this annealed feature, but if we can prove rapid mixing, that would be way cooler, but that seems to require much harder math tools. And then we also actually conjecture, I think many physicists have conjectured optimum actually is the same scaling, but it seems a bit hard to prove because you have to control outliers. And that would be my talk, and thank you for asking questions.
Two final questions.
So the optimization work is more like classical analysis of spin glasses using like grain descent or local message passing to. Can I say that?
Okay, so the analysis, right. The analysis is really analyzing kind of you can't do like a really like first order calculation. So we just calculate the average, the energy after some time. And then there's like a leading order piece and then second order piece. And then we somehow make sure that this guy is not too big. So then you can pick a very small time such that the first term dominates, which is this guy is kind of like an initial gradient. I don't know if that makes sense.
All right.
But it is like a very local and very perturbative analysis. It'll be interesting to compare with what, I guess, as what's your favorite classical algorithm would do in this case.
No, compare with the algorithm, just want to understand proof. Compare with the proof of the classical basis.
I have to check the classical proofs.
Should I run this on my 100 qubit logic?
Yeah, of course.
Can I?
Oh, I see. Yeah, why not? I think. Okay, so fermions might be a bit more expensive, but I think this K probably seems possible. And you might also need to sparsify because if it's like K is 4, it's n to the 4 many terms. That's a bit too many terms. But but there's you can also just sparsify all these models. You can make n like the number of terms being slightly more than linear in n. I think lots of probabilities will remain to hold, but one have to check with the so most of the probability will hold, but the circular lower bound would degrade. It will be bottlenecked by the number of terms sampled. But yes, you should definitely run on your common computer.
Let's thank the speaker again. Let's resume in 15 minutes. 3:40.